December 16th, 1944. Ardennes Forest, Belgium. Snow fell silently, blanketing the ground in frozen white. Inside a Sherman tank, 4 men waited, their breaths fogging in the cold air. The loader's hands were slick with oil as he lifted the shell 20 pounds of steel and death into the breach. Outside, somewhere in the mist, a Tiger tank prowled. The gunner whispered, "On my mark." For a heartbeat, time froze. The engine hummed, the forest was still, even the snow seemed to hold its breath. Then a thunderous roar. The shell left the barrel at nearly 2,800 feet per second. But what happens between that flash and impact? To understand, we must follow the shell itself from fuse to penetration. By 1944, the world was a laboratory of steel and fire. Battles were no longer decided by men alone, but by machines of engineering. Tanks roamed battlefields like iron beasts, and each shell they carried was a heartbeat, a promise of destruction. The German Tiger tank struck fear across Europe with its heavy armor and powerful 88mm gun. The Soviets relied on the T-34, mass-produced, reliable, and fast. The Americans focused on overwhelming firepower, supplying millions of rounds to the front lines. Each army's philosophy, speed, precision, or quantity, lived inside the shell. Engineers worked tirelessly in factories, turning blueprints into lethal reality. For soldiers, survival depended not just on courage, but on these pieces of engineered steel. Deep inside a munitions factory near Essen, Germany, sparks lit the air. Molten steel poured into molds, hammers shaped each cylinder, and machines stamped serial numbers into brass. Men worked in silence, soot-blackened faces illuminated by furnace fire. Every shell carried a precise combination of weight, length, explosive filler, and timing, engineered for a single purpose: destruction. Some were armor-piercing, designed to tear through Tiger or Panther tanks. Others carried high explosive charges to devastate infantry or fortifications. Among hundreds, one shell was selected, serial number 88472. Its journey had begun from the fire of the factory to the frozen Ardennes Forest. At first glance, a shell is simple, a cylinder of steel, but inside lies a symphony of engineering. The nose carries a ballistic cap for aerodynamics. Beneath it, the penetrator, dense steel or tungsten, delivers kinetic force. Around the base, the driving band grips the barrel, rifling, spinning the shell for stability. Inside, explosive filler and a tiny fuse await the right moment. Tracer compounds help the crew see its path. Every part serves a purpose. Metallurgy decides if it will pierce or shatter. Heat treatment determines behavior on impact. Even the paint on the casing codes its role in the battlefield. If the shell is a body, the fuse is its mind. Small, delicate, and hidden beneath layers of steel, the fuse carries the single responsibility of timing violence. It decides when energy becomes effect. In milliseconds, it chooses the difference between a dent and an annihilation. In World War II, frontline forces trusted a handful of fuse personalities. The simplest, the contact fuse, is blunt and immediate. It fires when resistance is met. The delayed fuse is subtler. It registers the hit, then waits a predetermined breath before detonating to allow the penetrator to cross the outer skin and explode inside. Time fuses count down to airbursts useful against unarmored troops or soft targets. Grazing fuses trigger when the edge of a shell scrapes a surface, preventing premature detonation when striking thin obstacles. To survive firing, fuses use clever safeties. Setback. Mechanisms use the violent jolt of acceleration to move a locking piece out of the way. Centrifugal arming exploits the shell's spin. Only after rotation reaches a threshold do weights swing outward, aligning detonators. These features keep rounds inert in storage, and only lethal after they leave the barrel. Engineers balanced sensitivity with robustness. A too sensitive fuse might cook off in transit. A too sturdy fuse might fail when it counted most. On freezing nights, in mud and ice, the battlefield was a cruelty test for tiny springs and delicate pins. Men learned to trust code numbers and color bands. They learned superstition as much as procedure. A single malfunction could tell a tragic story. A delayed fuse that failed to delay would detonate on the outer plate, wasting its energy in a bright but ineffective show. A contact fuse that failed to fire would allow the round to pass through armor and leave the interior intact. War is counted in small mechanical failures, the laughter of broken clocks. Men called it, all noise, no consequence. Fuse choice was doctrine. The Germans, experimenting with complexity, produced sensitive and capable mechanisms, but at higher production cost and greater risk of failure in poor storage. The Allies tended toward ruggedness and simplicity in many designs, trading a fraction of performance for reliability on the line. Those choices were invisible until they failed, and when they failed, the front line learned them the hard way. For crews, the fuse is faith contained in metal. They rarely think about springs and notches, they think about effect. Yet every pull of a trigger carries a gamble built by someone miles away in a factory, measured in millimeters and milliseconds. Everything compacts to this instant: the tally of training, the quality of metal, the weather, and the quiet arithmetic of distance. The trigger is a contract. When it breaks, chemistry becomes motion. A primer, small, precise, creates the initial flash. That flash ignites the propellant, a measured storm. Pressure spikes inside the chamber, measured in tens of thousands of psi. The only path is forward. The shell accelerates, pulled by an invisible hand, reaching muzzle velocities that turn tons of steel into controlled lightning. Recoil bites. The turret shakes. The instant of firing is not an image. It's a physical shock that reorders the body. For the loader, it's a heartbeat of survival. For the gunner, it is the sound of possibility, a target now contested by physics. At combat ranges, the missile's life is measured in seconds. A shell fired at 900 meters takes barely over a second to arrive. In that flash, all variables must align: spin, velocity, pitch, wind. Barrels wear with use, changing ballistics subtly. Crews fought both enemy and time. Every extra 1,000 rounds down the barrel changed the odds. Rifling imparts spin via the driving band. Spin stabilizes the projectile like a thrown football. Some rounds, subcaliber penetrators or APCR, use sabots, lightweight carriers that fall away after leaving the muzzle, allowing a smaller, denser core to fly faster. Others rely on mass. A longer, heavier penetrator delivers more kinetic energy to overcome armor. The shot is also a ritual. Commands clipped, hands practiced, eyes trained to watch. They measure hits, adjust for wind, and reload. There is no time to exult. War offers no applause, only repetition. Another round is chambered. Another decision is made. Every shot leaves behind an answer. Sometimes it is a smoking hull and silence. Sometimes it is a bounce and more planning. The shell does not choose. Its design only influences chances. The soldier chooses to press until the odds are in his favor. Once free of the barrel, the round is a small, stubborn world. It flies through cold air that bites its surfaces, through dust and debris that attempt to nudge it from course. That flight is ordinary physics and tiny miracles. The maintenance of trajectory over hundreds of meters, against 1,000 distractions. Air resists, drag decelerates. The slender shape and ballistic cap fight this, smoothing airflow to preserve velocity. The shell's spin resists yaw, that tendency to tumble, keeping the core pointed where it must go. But spin also complicates certain fuses and shaped charge rounds, which require different stabilization methods. Tracers are the human piece of flight. A small pyrotechnic column inserted into the base tells the gunner where shots land. They burn for a few hundred meters, a bright line that allows correction. At night, these tracers carve the dark into visible geometry, arrows of intent and error. External ballistics is a war of decimals. A 2-degree misalignment at the muzzle can mean a miss at the target. Temperature changes the gas pressure. Barrel fouling alters velocity. Even the Coriolis effect plays a role at extreme ranges. But at the gritty ranges of WWII armored duels, it was often the human adjustments and the quality of manufacture that decided the shot. And then the world narrows to a face of steel. Time stretches and compresses. For the tank being shot at, the impact is not a slow revelation but a single, devouring punctuation. For the shell, it is the final act of a journey that began in heat and precision. Flight is both promise and gamble. Every meter traveled is a negotiation between design and chaos. When design wins, steel yields. When chaos wins, it does not. Our shell, serial 88472, now approaches the Ardennes clearing. Its fate aligned with a single aim and 1,000 small choices. We have looked into the tiny mind of the fuse, felt the gun's thunder, and watched the shell cut through the void. The rest is consequence, penetration, spall, and the human moments inside the burning hull. That is where we will go next, into the 1 second when engineering becomes fate. Impact is not a moment. It is a microcosm of war, condensed into a heartbeat. When a shell strikes armor, it unleashes energies that no human can endure. Kinetic force collides with resistance, steel meets steel, and physics becomes violence. A penetrating round carries thousands of kilojoules of kinetic energy. It does not simply make a dent. It fractures, peels, and sprays interior metal fragments with lethal precision. The outer shell of the tank may survive visually intact, but inside, the world has already changed. Even a round that fails to penetrate transmits shock through the armor. Bodies are thrown, eardrums ruptured, equipment shattered. Every millisecond counts, and every tiny fraction of a second is measured in human lives. For a crew inside the tank, there is no anticipation, no preparation. One instant they exist, the next they are engulfed in a maelstrom of force, heat, and metal. Time stretches and compresses until a single heartbeat feels like an eternity. Confined spaces amplify every effect. Heat rises, pressure builds. Flames curl along metal surfaces, licking oil and fuel. Ammunition cooks off like a chain of miniature bombs. A tank becomes its own furnace, steel bending and twisting, war's mechanical bellows breathing fire. Each fragment moves faster than bullets, tearing flesh, rupturing hydraulics, puncturing fuel lines. The crew has no time to react. Even a trained tank commander cannot escape the mathematics of physics and the precision of engineering. Survival is measured in chance, luck, and the smallest margin of error. Smoke chokes the compartment. Heat sears. Systems fail. Fire suppressors, if they exist, buy seconds, not mercy. The tank's very geometry becomes an enemy. A moment ago, it was a weapon. Now, it is a tomb of twisted metal and noise. Tankers called it a brew-up. Casual words, masking horror. To see one of your own burn, to feel the blast echo across the forest, to smell smoke and oil, is an experience that imprints itself on memory permanently. From outside, it may appear simple. A smoking hull, silence, and emptiness. But inside, the story is chaos compressed. Engineering, violence, and human lives intersecting in fractions of a second. Every shell fired is a question. Every impact an answer, one calculated in kinetic energy, doctrine, and chance. For the engineers, success is the shell performing as intended. For the gunner, it is survival. For the crew struck, when they survive, it is chaos made manifest. War reduces all to numbers, angles, and fractions of a second. Yet it is also emotion, terror, and endurance. And so the story of a single shell ends, not in explosion alone, but in echoes. Metal bending, fire spreading, lives altered forever. The battlefield records each outcome, a ledger of physics, courage, and fate, and waits for the next shot. War leaves behind fragments, metal, fire, and stories. One shell, forged in fire, guided by science, fired by a hand trembling with focus, has passed through life and death in a heartbeat. Its journey begins in factories and ends in moments that decide fate. In that journey lies the legacy of engineering, courage, and chance. Tanks and shells were the titans of the battlefield. They dictated strategy, altered terrain, and measured human resolve. Yet behind every round fired there were men, creators, loaders, gunners, engineers, each intertwined in the mechanical ballet of destruction. For the shell, it is simply function. For humanity, it is consequence. The shell's story does not end at impact. Its effects ripple through time, influencing battles, shaping tactics, and inspiring innovation. Lessons were learned in mud, ice, and fire. The design of a simple piece of steel evolved over decades into modern penetrators, sabot rounds, and precision munitions, technology built upon the foundations of survival and necessity. Every piece of war machinery tells a story. Every shell carries intention and consequence. And every one that flies, spins, and strikes leaves behind echoes, echoes of engineering, echoes of courage, and echoes of the men who lived or died by its journey. In the end, the story of a tank shell is the story of war itself, precise, brutal, and unforgiving. In World War II, the life expectancy of a tank crew on the front lines averaged less than 6 weeks. Every shell fired carried not just destruction, but the weight of human lives and history.